In this video I demonstrate Pearson's R correlation. This type of analysis is appropriate for gauging the association, if any, between two interval variables. Now, when running correlations on two or more interval variables, there are two command options, listwise or casewise deletion and pairwise deletion. I'll assume here that you know the difference between the two. I'll be using the following variables to illustrate Pearson's R correlation. I have a state-level data set I created from the Kids Count website, which compiles statistics related to children, including demographics, economic well-being, health, and so on. As you can see in my Variables Manager window, I have 2010 state-level data on the percent of children in extreme poverty, those living in households making less than 50% of the federal poverty line, the child death rate per 100,000, the percent of kids in single-parent households, and the infant mortality rate per 1,000 births. All of these variables are interval measures. While the commands for both listwise and pairwise correlation are quite simple, allow me to show you how to run both through the menu system. In all likelihood, you'll easily remember these commands and simply type them into the command bar in the future. So first we go to Statistics, Summary Tables and Tests, Summary and Descriptive Statistics, and here's where we see our two options for correlation. First, we have correlations and covariances. This command conducts the correlation using listwise deletion. It has a few options and simply runs a bare-bones correlation analysis. Alternatively, you may choose the next option down, pairwise correlations, which uses pairwise deletion. The pairwise command allows for many valuable options and will probably become your go-to command for running correlations. But first, let's run a plain listwise correlation analysis. I'll simply insert the variables that we're going to look at. I've included all four here, and we'll go ahead and hit submit. You can see here's the basic command, correlate, and then the four variables. And you get a bare bones correlation matrix, correlation coefficient between each pairing of variables. Now let's go back to the menu and choose the pairwise correlation option. Here we have a lot more options. Again, I'll insert all four variables. Now let's take a look at the options. First, print number of observations for each entry. That will give us the n, or sample size, for each correlation analysis. I'll go ahead and check that. Next, print significance level for each entry. That will give us a p-value for each correlation coefficient, indicating whether we can be confident that the correlation in the population is not zero. I'll go ahead and check that. Next, we see an option to use listwise deletion. That basically means we can ignore the other correlation command and just remember this one. Should we want to run a correlation using listwise deletion, we just need to indicate that as an option. I'll go ahead and check that. Finally, we can ask Stata to include a star or asterisk if the correlation is statistically significant at the 0.05 level. That's a little redundant given that we've already asked Stata to print significance levels for each entry, but I'll include it so you can see it in the command. I recommend ignoring the significance level adjustment at the bottom. So let's go ahead and hit OK. First, let's take a look at the command. It's pretty simple. It's simply pwcore, and then your variables, comma, and then here's where we have our list of options. OBS told Stata to include the number of observations for each correlation analysis. SIG told it to include the p-value. Listwise told it to use the listwise deletion technique. And star parenthesis 5 parenthesis told it to include an asterisk if the correlation coefficient was significant at the 0.05 level. Looking at the results, the first number listed is the correlation coefficient. An asterisk indicates the coefficient is significant at the 0.05 level. I'll say more about these coefficients in just a bit. The second value indicates the p-value for that coefficient. Finally, the third value indicates the n, or the number of observations in that particular analysis. Note that they're all 47 here because I included the listwise option in the command, thereby standardizing the sample for all of my analyses. Let me rerun the analysis but exclude that option. I'll simply remove listwise from the command line. Now we can see that the number of observations vary a little across analyses, ranging from 47 to 51. 51 because I've included DC in the analysis. Now, how can we characterize correlation coefficients? First, it's important to note whether the coefficient is positive or negative. A positive coefficient indicates that the variables vary in the same direction. A negative coefficient indicates an inverse relationship. In other words, as the value of one goes up, the value of the other tends to go down. Next, we look at the coefficient itself, which is a measure of effect size. While there are no hard and fast rules, we might use the following very rough guidelines to characterize the relationships indicated by the coefficients. Now I'm indicating absolute values here, so anything greater than a 0.05 in absolute value could be characterized as strong. You could use qualifiers like very strong and so on. Anything in the 0.3 to 0.5 range is considered a moderate relationship, and anything in the 0.1 to 0.3 is considered weak. Again, those are just very rough guidelines. Another way to characterize and understand the correlation coefficient is to calculate what is known as the coefficient of determination, or COD. The COD is the proportion of variance in one variable that can be accounted for by another variable. Mathematically, it's nothing more than Pearson's R coefficient squared, or R squared. Let me illustrate that using the correlation coefficient for extreme poverty and infant mortality, which has a correlation coefficient of 0.6723. We can simply use Stata's calculator to do this, and it's simply the command display, and then let's go ahead and type in 0.6723 asterisk for multiplication symbol, 0.6723. Alternatively, I could use the hat 2 for squared. Go ahead and hit return, and we get a COD of 0.452. Now we could also have gotten the R squared by running a simple regression between the two variables. In that case, it's a simple command, simply regress, and we'll do infant mortality against extreme POV. And here's a simple regression results, but notice the R squared, 0.452. So what does the R squared tell us? It simply says that 45.2% of the variation in one variable can be accounted for by variation in the other. In this particular case, I can say that 45.2% of the variation in infant mortality across states is accounted for by state variation in my extreme poverty rates. In a subsequent video, I'll demonstrate the scatter plot and fitted line. These help to further visualize the relationship between two interval variables.